Big data is cursed. We're going to look at two curses in particular, the curse of dimensionality, the curse of phantom information. So let's look at what we've seen so far. Big data is high volume. These can be incredibly large data sets, high variety, many interdependent processes, producing many different types of data. So every big data problem is unique. So why not just avoid big data? Use better data collection, better sampling techniques, so forth. Well, there's an upside to big data. High volume means lots of useful information, lots of actionable information. Results are reproducible, reliable, and robust. High variety means no limit to what we call data. Images, tweets, documents, automobiles, airplanes. We can study and analyze very complex structures in data. In other words, we can do things that we've never been able to do before. There is a downside to big data. High velocity. Data can occur so quickly or be so large that algorithms run just too slow. For example, the subset sum problem. Given a set S of positive and negative integers, find the largest subset whose sum is 0, if one exists. For example, this set S, it's pretty obvious the first two sum to 0, and you can check that these 6 numbers sum to 0. And suppose you had only 250 integers. Well, that's 10 to the 75th subsets. That would take more than 10 to the 51st years on what used to be the fastest computer in the world, the Titan supercomputer. And big data is cursed. There's two issues we're going to explore. There are others. In a high-dimensional space, a nearest neighbor may be very far away and rather isolated. The more space to search, the slower the algorithm. The farther apart, the less reliable a relationship between 2 points in that space. Where high dimensional means that we're looking at a large number of variables that are responsible for the data. So first, what is a variable? Well, a variable X is always associated with a set S, which means a trial of X is an object in S, and every object in S can be a trial of X. So if S is a set of objects, then a trial is an object in that set. A variable can be regular, random, or chaotic, which means random-like, but not actually random. Variables X and Y are independent if the value of X does not depend on the value of Y and vice versa. So the curse of dimensionality is that we tend to have, first off, very high dimensional spaces, many independent variables, because there are many independent processes sometimes, and there's often a need to embed in a very high dimensional space, so we can use linear methods and get linear separability. So there are two issues due to this curse of high dimensional spaces. Data points become increasingly isolated as dimensionality increases, and averages tend to drown out useful information. For example, let's look at hypercubes. Suppose we had variables x sub j, j equals 1 to n, where x sub j is either true, which is a 1, or false, which is a 0. These could be called also factors or features. An n-dimensional hypercube is the set of all points in Rn whose coordinates are either 1s or 0s. So observations are adjacent if they differ in only one factor. So here is a 2-dimensional hypercube, and here's a 3-dimensional hypercube. What is the maximum number of steps between observations of points in a hypercube? This is also known as the diameter of the data. Well, we can take 2 steps, and that's the farthest we can go between 2 observations or vertices of the hypercube. In 3 dimensions, we could take 3 steps. So we have a diameter of 3 steps, largest distance between points in a hypercube in 3 dimensions. So the line segment from the origin to all ones is the main diagonal of a hypercube in any dimensional space. And you have to take n steps to go from all zeros to all ones. Also, what is the angle between the main diagonal and an axis for an n-dimensional hypercube? Well, for 2 dimensions, it's 45 degrees. For 3 dimensions, it's 54.7 degrees. And notice as n becomes larger, the angle approaches 90 degrees. So hypercube is much simpler than most big data. However, 2 observations of n factors can be as many as n steps apart, and n can be incredibly large. An angle between an axis and the main diagonal approaches 90 degrees as n becomes very large. Big data is even worse. You have the data spread out across enormous distances in which any 2 observations are practically uncorrelated, i.e. at 90-degree angles. This is the curse of dimensionality. There's also a curse of phantom information. Often big data contains at least some random noise, which means studying random variables. And randomness may or may not be important. Random-like patterns may be the answer to your question, or they may be misleading, or they may be just there. And if you have a sufficiently large data set, you can find almost any pattern in that data. So independent and identically distributed. X is a real variable if it's associated with the set of all real numbers R. A trial is an instance of X, in other words, a sample of X. If all the trials in a sequence are of the same X, then the trials are said to be identically distributed. And if each X sub j in a sequence occurs as if it were the only trial conducted, in other words, it depends on no other trials, then the trials are independent. The sample mean of X over n trials is simply defined to be the sum over those trials divided by the number of trials. Now, a real random variable X is ergodic if its properties can be obtained from at least one sequence of trials of X. So X is ergodic if it can be estimated from data. Obvious why we want to consider ergodic variables. But there's a non-obvious reason. If X is chaotic and not random, then there's a set S called its attractor on which X is ergodic. In other words, any ergodic variables can be studied using data. So the law of large numbers says that if X is an ergodic random variable, then there's a number mu such that the limit as n goes to infinity of the sample means of X is equal to mu for almost every identically and independently distributed sequence of trials. This number mu is called the theoretical expectation of X, or the expected value, written like this. Now, it is possible to get a sequence of trials that doesn't satisfy the law of large numbers. For example, a sequence in which every trial is 2 mu. But such sequences occur with probability 0, quote, in the real world. That's why we say for almost every. So the law of large numbers is a special case of the mean ergodic theorem, which intuitively says that if X is ergodic over a set S, and you have a sequence of trials that's independent, then the average over the sequence is the same as the average of X over S. And this allows us to look at chaotic variables also satisfying the law of large numbers in the sense of the mean ergodic theorem. Let me show you an example here. So as we take samples of our chaotic variable, we get what we get with the law of large numbers, convergence of the sample means to a theoretical limit. But high variety often means that complex data is from trials that are not independent. However, identically and independently distributed sequence of trials are very important to us because they're going to allow us to use probability and statistics. So let's look at identically and independently distributed in the law of large numbers and how that gives us probability. Suppose you have a real variable X and a subset of the real numbers A, and an identically and independently distributed sequence of trials of X. We're going to define the count after n trials of A to be the number of trials of X that are in A in that n trials. We're also going to define a variable y sub A to be 1 when X is in A and 0 otherwise. Then we can take a sequence of trials of the y's. The expected value of the y's, the sample mean I should say, of the y's is the same as the count over the number of trials. In other words, the theoretical expected value of y sub A is a limit as n goes to infinity, c sub n, the count of the number of trials in A over n. And that gives us a definition of probability. The expected value of y sub A, which is the relative frequency, c sub n of A over n, is defined to be the probability that X is in A, which we write like this. So this gives us the probability of an event. Conduct n independent trials of an experiment. So a random process is often just called an experiment. If A is an event, then count the number of times we get trials that are in A. The probability of A is defined by this limit as n goes to infinity of the count over n. This is often called the relative frequency. And notice here our n is very, very large. It's going to infinity. For example, if A is the possibility of heads with a fair coin, then about half the time we flip the coin, we're going to get heads. And that means the count is about 1/2 n as n goes to infinity, because the probability of a fair coin being heads is 1/2. Let's look at some examples with just coin tosses of different probabilities. So here we are looking at a probability of 1/2. And even though to begin with, we've only got about 100 trials, we're not there, but as we get even into a few hundred trials, we start seeing the relative frequencies settle into the theoretical expectation. And after 50,000 trials, very close. So what if the probability of heads is 25%? Well, again, it doesn't look close, the sample means don't, to the theoretical average or theoretical probability of 25%, but in the limit, we get there. Even for a very small percentage of heads, so it takes a long time before you actually get one head. However, in a relatively short period of time, the relative frequency again converges to the theoretical probability. So big data fights the law and wins. Events with probability 0 can and do appear to occur in big data sets. Let's illustrate that with sort of a thought example. Suppose a tossed coin lands balanced on its edge no more than 1 time in 1,000 tosses, no more than 2 times in 4,000 tosses, no more than 3 times in 9,000 tosses, no more than n times in 1,000 n squared tosses. Then the probability that the coin balances on edge is less than or equal to this limit as n goes to infinity over n over 1,000 n squared, and that limit goes to 0. So we're saying the coin balancing on edge has a probability of 0, even though we may see it a number of times in a very large number of tosses. So here's an actual data set, and we're going to say NA means we have a missing value for the outcome of the coin because it balanced on its edge. And even though the probability of NA or balancing on edge is 0, we could possibly see in our data set here as many as 100 missing values or balancing on edge outcomes. In fact, up to 10% of the observations could contain trials where a heads-tails outcome is not available, even though the probability of not available is 0. So big data is high volume unavoidably because of the high variety of patterns. And such high variety means that big data often cannot be interpreted as independent trials of independent variables, and that there may be many missing values in the data.